So really quick, going over your do now. The do now was kind of reiterating to you guys by now. Maybe you have, or maybe you haven't have, maybe you have or have not recognized the pattern to find the growth factor when giving more than one value. If you have, great. If you have not, then this is what we're doing. So when you're finding your growth factor, um, do you guys remember where we talked about for exponentials and logs, their relationships change, right? For an exponential function, you have a multiplicative change in your y values, right? Your y values are doubling or tripling. And so the multiplicative change means that in order to find that change, I have to divide my y values, right? If it's multiplicative, then I have to divide my y's in order to figure out what was the change that led me to this. Does that make sense? Okay. So when we're talking about exponentials, that's y equals a times b to the x. And when you're finding your growth factor or your decay factor, basically your change factor, right? In order to calculate that, as long as you have 2 points, you're finding the quotient between their y's to the power of 1 over their difference in their x's, okay? So when you were given this problem, you had day 0, we have 10 bacteria colonies in a petri dish. So when I'm thinking about my table, I know at day 0, there is 10. On day 4, there is 20. So I have an X and a Y that's being given to me. Do I have enough information to figure out what that growth factor is? I do. I have 2 X's and 2 Y's. And how many are required here? 2 X's and 2 Y's. Remember, your A value is going to always be your initial. So I already know what A is. I know that A is 10. What's left for me to find this model is by finding y2 over y1. Now, granted, do we know how to do this in the calculator with the regression model? Yes. This is showing you that you can do it without the calculator, okay? You're going to end up putting something in the calculator, but you're capable of calculating this as far as you can on your own without creating a regression model, okay? So when I'm plugging this in to find my B, you should have done 20 divided by 10 to the 1 over 4 minus 0. Literally is what it's telling you to do. Take your X's, take your Y's, plug them in. And you should have gotten the approximate value of what? Anybody? Everybody? Is that what we got? So do I have everything I need to write my model? Yes. So your model should have been y equals 10 times 1.19 to the x. And could I figure out from there how much the bacteria is growing? A little by little every day, okay? So this is just kind of showing you that you have the tools to do this. We have to remember that because it's a multiplicative change, the opposite of figuring out what I multiply by is to divide. And you have to keep in check that how your x is changing. If your x's aren't changing consecutively, like 1, 2, 3, 4, 5, 6, 7 by a change factor of 1, then you have to take into account what that change factor is. And that's why the power becomes the difference. Okay. All right. Questions, comments, concerns. All right. So this leads us into today's class practice. So our class practice is going to work like this. There's going to be problems on the board. And as these problems come up on the board, you're going to work in your group to see how far and how much you can get done and talk about and process over the course of that 1 to 2 minutes, well, 2 to 3 minutes that are allotted to you. Does that make sense? Okay. Then we're going to come back together and we're going to discuss to see how far and what you and your class did, your table did. Now, this is a low stakes practice because it's not for a grade, but it is something that you should want to actively try and do because it is leading you up to the test. And these are things and types of problems that are going to be on the test. Got it, Val? That's why we should be sitting at our desk, not on the couch. And so with that, the goal is not to just calculate logs and exponentials, but our goal is to be able to apply them to real world scenarios and applications. Okay. So again, this is low stakes, not for a grade. It's strictly for practice and exercise to make sure that we're comfortable with what we're doing. I am asking you to talk and to discuss with your group the problems and to compare and contrast what you got and what your thought process was to lead you to certain things. Okay. So we're going to start with problem number 1. Problem number 1, you have Carmen here, and Carmen is investing. So what I'm going to give you, I'm going to give your group a few minutes to start. Can y'all close the door? I'm going to give your group 2 minutes, 3 minutes to do 3 minutes. For 3 minutes, you're going to read through, identify important information, and then answer part A. Okay. If your group finishes before the 3 minutes is up, I then want you to try and answer part B. We will reconvene to do part B together. But if you finish before the 3 minutes is up, then I would like for you to challenge your group to do part B. Okay. Capiche? All right. Again, low stakes, no stakes, just you practicing with the material and expressing and showing what you know. All right, so 3 minutes is on the clock and go. Okay. All right, so let's see. Group 1. What is the independent variable here? What? Years. Okay, so we know that our independent variable, which is typically our x, but in this problem it's not, is the years. Okay, and by default, therefore, the dependent variable is going to be, which is our y, represents the what? The money, your balance, right? Okay, I point this out because when we're putting this into Desmos, can I put it in with A's and N's? The answer is no, I cannot. I have to put it in with Y's and X's or F of X. So when I'm putting this into Desmos, I have to be sure of what's my independent, what's my dependent. So we have Y equals 500 times 1.02 to the X. So if I'm looking for A of 5, I'm looking for when does, I know this is terrible notation, but we're looking for when does Y of 5 happen? Meaning what is the value of 500 times 1.02 to the 5? That's simply all it was asking you, right? And it's saying, what does that mean in terms of the problem? So in terms of the problem, we're asking after 5 years, the balance is ... correct? That's what it's saying in terms of the problem. So when we come to our handy dandy Desmos, I'm going to refresh and clear her all out. That's where we had our Y equals 500 times 1.02. And because it's only one singular value, I can simply put it to the 5th, right? If I have multiple values, that's when I would want to use the actual function itself, right? So that I could use a table or use function notation to calculate. Okay. All right, so we ended up with $552.04. So our balance, $552.04. All right. Easy enough? Lily? All right, the next part is saying, what if I don't deposit any more money and I want to know how long will it take for me to get to $1,000? Okay, what it's now saying is that your input is now going to be your balance. Does that make sense? So our independent and dependent variables are switching. So what ends up happening is you see how this is here and this is here. When you're switching, because you're changing what you're inputting, it's going to become x equals 500 times 1.02 to the y. And now our job is to create a new model where this is no longer there. So the goal here is to get y by itself. And then you can plug in that 1,000, you can plug in 2, you can plug in whatever, but you're finding the inverse of it, okay? How many of you guys remember PEMDAS? Please excuse my dear Aunt Sally. Okay. PEMDAS is when we're evaluating, right? We go in the order of PEMDAS to evaluate. When we're solving, we're going to go backwards. I like to call it SAD mapping. We're going to SAD map, okay? So you're going to work to get y by itself, and you are working backwards. So you're asking yourself, is there anything that I can add or subtract away to get y by itself? And the answer here would be no. Next step, is there anything I can multiply or divide away to get y by itself? And the answer would be 500. So I can divide both sides by 500. So now we're left with x divided by 500 equals 1.02 to the y. Okay, as we're working backwards, we're going to ask ourselves, we're at the e in PEMDAS, we're at exponent. How can I set an exponent free? Well, this is an exponential. What is the inverse of an exponential? What would I use as the inverse? Log. I'm going to use log as the inverse here. It wasn't on part A. We did not touch log at all. So we're going to use the inverse of this. And the inverse is you can use any log your heart tells you want to. However, if I want to do it in the least amount of steps, I'm going to use a log of the same base as my exponential. Does that make sense? Because it's going to cancel out my base. If I use a log of the same base that I currently am, then this base gets to go away. So we have log, that got weird, base 1.02 of x over 500. And what that does, it now eliminates the base of my exponential, and my y is now set free. So this is my inverse model. This is my inverse. Now I'm telling you that the number of years n of a. Does that make sense? I don't know why I made the n a capital letter. And that's what this equals. So if I want to know what 1,000 is, I'm now, how many years will it take my amount to be 1,000? And I'm setting that equal to this. Not equal, I'm plugging in now for that variable. Does that make sense? So your quantity has changed. And so we're going to look at this graphically to see the difference in the two. Okay? I'm going to go back to my Desmos to show you why they are inverses. All right, so you see how I put the 5 here? I'm going to switch this one back to an x. And now I'm going to put in its inverse. Y equals log shift dash 1.02 x divided by 500. And we're going to look at the graph. What do you notice? They're inverses. They're reflected over that imaginary y equals x line. So that y equals x line is how we can see that visually we're dealing with inverses. Okay? If this didn't happen visually, then that tells me that the equation I created isn't my inverse. It isn't going to give me that value that I need. Okay? When you're looking at the table, I'm going to open the table for both of them. So look at the table here. What value did y'all put in? 5, right? I'm going to switch this to 5. And we'll let you be 6. Okay? So I can put in 5 and 6. On this one, I'm not putting in 5 and 6. I'm putting in my amount. So notice how when it's so small, it is undefined or negative. That's because this is now your amount. I have to be at 500 to start. Because that's what my initial balance was, right? So 0 years, I have $500 in my account. If I want 600, it's going to take me how long? 9.2. So if I want 1,000, how long is it going to take me? 35. If I want 2,000, it's going to take me 70 years to not add any more money to that. It's a very low interest occurring savings account. Don't do that. If I want 3,000, I will be long. I will be gone. It's going to take 90 years. Okay. And as you can see, these are inverses of each other because they're calculating different things. All right. If I wanted to know how long it would take me to do 520 and how much? 20 cents. If I typed 520 and 20 cents, what value should I get? I should get 2 because they're inverses of each other. And inverses means that your input and your output are switching. Your independent and your dependent are switching. So what you're searching for has now changed. Yes? No? Maybe so? Do you all see that? I really wish I could read your mind, but I can't. So if you are confused or have a point of confusion, you kind of have to tell me. Otherwise, you're my green light, and I'm assuming we're good to go on. Did you set it equal to 1,000? So let's say you went here and you're like, well, I need y equal 1,000. You're going to get that answer wherever y is equal to 1,000 at. He just left. So you may have did it. I'm not at 1,000. Yeah, I'm asking you, what did you do?
Just typed in numbers until it said it.
Yeah, don't do that. Don't do the guess and check. There's too many ways for you to do it without guessing and checking. Because your numbers could be too large and then you were stuck. So I wouldn't encourage you to do that ever again. Yeah. All right. The other way is did anyone actually set the original equation equal to 1,000? Okay. You could also just set the original equation equal to 1,000 because it's only one value you're searching for, right? This one, finding the equation now allows you to solve for more. So when I say you took 1,000 and you set it equal to 500, parentheses 1.02 to the x, and what are we still doing? We're still dividing by 500. Correct? After we divide by 500, we're left with 2 equals 1.02 to the x. What is the inverse of 1.02 to the x? Log of the same base, log of 1.02 of 2. That cancels out our base, and we're left with x. Guess what that's going to still tell you? It's still going to tell you that the answer is how long? 9 and some change, right? You still ended up not 9, 43 and some change. And it still take you about 43 years to make that because that's what this ends up. Does that make sense? So it doesn't matter which way you did it, but guessing and checking shouldn't be the way you do it because that's going to take you a little bit longer. I don't know how you guessed and checked all the way up to that amount, but yeah. So just thinking about that, that's why we have rules and inverses. Okay. Guess and check should be the very last thing you do, like your last Hail Mary. All right. Okay. So if you guessed and checked, I'm going to encourage you to not do that on the next one and see how it goes. Okay, so I'm going to reset Desmos. I'm going to go back to our problem, and here we go. So on this one, you're going to read, you're going to go through, and I'm going to give you time because you're also going to find the inverse, okay? So this one, you're going to have a little bit longer. So I'm going to give you about 5 minutes to go from part A and part B. On part B, you're creating the equation, okay? So there's no values. You're just finding the inverse equation that works. So think again, we're switching our independent and our dependent. All right. So we're going to set our timer, give you your 5 minutes. and go. Okay, so on the first part, you are given f of 0, f of 3, f of 7, f of 10, f of 14. This is simply function notation to tell you to do what? Substitute. That's exactly what that means. When you see this, this just means to substitute. Plug and chug, right? We're substituting those values in. So when I'm looking for f of 0, I'm going to plug in 0 for t. When I'm looking for f of 3, I'm plugging in 0 for, so I'm plugging all of these in, f of 3, f of 7, f of 10, and f of 14, okay? Because I have multiple of these, do I want to have to plug them in 5 times? No, I don't. And if I don't want to have to plug them in 5 times, then I'm going to do what? Look at the what? The table, the handy dandy table, okay? And I have to understand, what is my independent? Well, your independent should have been your t, right? Your time is your independent. How many days since the beginning of the experiment? And your output is the number of bacteria of the colonies. So all these answers are going to be colonies. How many colonies do you have? How many colonies do you have? How many colonies do you have? Okay. So let's go look at our table, or putting in our table. So I'm going to first put in my equation, and our equation, I can't put in anything other than f of x or y. Doesn't matter which one you do. No, you just can't put in f of t. So I'm going to put in f of x, and f of x equals 10e shift 6 to the 0.24x. So notice again, I couldn't put in the t. I'm going to click on the little gear table, and I'm going to put in the values that I'm looking for. I know 0 is there, but I want it at the top. So I'm going to put 0. I have 3. I have 7. I have 10. And I have 14. Now I have found out exactly how many colonies after a set amount of days exist now. Bacteria colonies exist. So after day 0, I'm at day 3. On day 3, there's 20.5 colonies, right? On day 7, there's 53.6 colonies. On day 10, there's 110.2 bacteria colonies. And on day 14, there's about 287.9 bacteria colonies that exist. Okay? How do we feel about multiple functions to evaluate at a time and using the table to do so? Did anyone substitute in for x 5 times, or did we all go to the table? Multiple substitution table. Okay, I'm going to pretend that we all use the table. All right, the next part was finding your inverse function. So the next piece was finding your inverse, because it says write a log function g such that g of p equals t is the number of days since the beginning of the experiment. It will take for the number of bacteria colonies to equal p. So it wants you to find the log of this, which means that we're taking our initial, and we're taking the initial, and we're switching our input and our output. So now t is our output, and we have 10e to the 0.254, whatever it is a 5 or 4? 4. 4. Okay, I can't accept it. It looks terrible. And this is now going to be our P, our population. So the goal is to now get P by itself, because we switched our independent and dependent, and we're doing what again? SAD mapping it. We're going backwards, right? So the first thing I ask myself, is there anything I can add or subtract away? And I'm going to tell myself, no, not this time, homie. Then I'm going to go into the next. Is there anything I can multiply or divide away? I'm like, oh yeah, you can. Which one is it? What can I multiply or divide away? I can divide by 10. So now I'm down to t divided by 10 equals e to the 0.24 p. All right, we're down to the exponent. What is the inverse operation of e, of base e? Huh? ln, natural log. So I'm going to take the natural log. This is your natural base. In order to get rid of the natural base, you have to use the natural log. And what that does is cancel this bad boy out, and I'm left with 0.24p. And then we start sad mapping all over again. Is there anything I can add or subtract away? Nope, but there is something I can divide away. And boom, p is now by itself. So this is my inverse operation. This is what g of p is. So g of p, which it says is equal to our t. What that means is that instead of putting in time, you're now putting in the population, right? So if I had a goal population of knowing, when will I have 1,000 bacteria colonies? I would just plug in 1,000. The main thing here is that you're finding the inverse. All right, number 3, we're going to go together just so that you can have time to start working on the 3A.3 assignment. So we're going to do number 3 together. Some of your pages got printed real weird. I did try to reprint them, but then I was like, I'm wasting paper, and I thought I canceled it. So there are some corrected papers. They're just okay. We're going to do a little popcorn reading. So who would like to start us off popping? I love it. Pop.
States that every 1.5 years, the number of
Perfect. Too many theater people here for y'all to be quiet.
The number of transistors on an integrated circuit provides a good measure of the speed of computers which make calculations using integrated circuits.
Pop.
In other words, every 1.5 years, computer speeds up.
1970, approximately 1,000 transistors could fit on an integrated circuit.
Perfect. All right. So what this is talking about is how computers have evolved, right? So your integrated circuit, anyone wants to go into computer science or computer engineering? Anybody? Nobody? No? I find this interesting because for a moment I thought this would be a fun thing. Oh, Ezekiel? Computer science, computer engineering? I guess. Okay. So this is useful. This is interesting because computers are constantly changing and growing and evolving. That's not just computers, but technology in general. Think about how quickly a new phone comes out with just a little bit of change, right? That's because of how these circuit boards are being developed and what they're able to condense and make big, make small, and change the capacity up. So what the Moore's law describes is a general effect of how we have evolved and how this changes. So from this problem, it tells us the growth that's taking place, and it explains to us what our situation looks like. So we're going to start off with our independent variable. Our independent variable here would be our time since 1970. 1970 would be our beginning, our 0. Does that make sense? Okay. And in 1970, a computer could only process a transistor with have a computer process, can't talk, computer speeds were only processing about 1,000, right? So, and it said here that every 1.5 years, it did what? On average, it does double. So if in 1970, which is our 0, in 1.5, that becomes what? 2,000, because the transistor power has doubled. From this alone, do I have enough to establish what my exponential function could be? I do have enough to establish. I have enough to establish not using regression models, but actually just calculating. Your do now today was kind of a way to lead you into being able to calculate your B by hand. Okay. So we're going to use that, and then we're going to double check ourselves with our regression model. Is that cool? All right. So starting off, your A always comes from your initial value. What is our A? 1,000. So A is done. All right. Next, we got to find our B. Our B equals our Y2 divided by Y1 to the 1 divided by X2 minus X1. Do I have enough to calculate my B? I have 2 Y's and 2 X's, so I have plenty. So we have B equals 2,000 divided by 1,000 to the 1.5 minus 0. I can clean this up a little bit, and I get 2 to the 1.5. Because 2,000 divided by 1,000 is 2, and, sorry, my 1. And 1.5 minus 0 is 1.5. And now all that's left is to plug that into the calculator to get an approximate value, okay? So we're going to plug this in to get our approximate value. So I'm going to go back to my calculator. I'm going to refresh her, and I'm going to type in 2 shift 6 to the 1 divided by 1.5. And I get that my B value is approximately 1.587. Do I have all the parts to write an exponential model? Yes. So we have 1.587. So our exponential model would be Y equals 1,000 times 1.587 to the X. Okay. Was that terrible to do without a regression model? It was. It was so terrible. Oh no. Yeah. It was. Okay. Let's do a quick refresher of the exponential model. In order to do an exponential model, you have to have a table. So I've made a regression model. So I have a table, and I'm going to add the table. At the table, put in my values. We have 0, 1,000, we have 1.5, and we have 2,000. Bam, there she goes. I'm going to run the regression, and I need an exponential model. Oh my gosh, we're geniuses. That's crazy. It's exactly what we got by ourselves. Who knew? Okay. So we're good. We did awesome. All right. Now, I am going to copy this so it can save it for me because I'm going to take away the table. So there's our model. Check. That's our exponential. The next part asks us to create a log model. Okay. If I wanted to make a log of this, what's going to happen is a couple of things. We're going to do it by hand, but I'm going to show you what happens when you try to do the log using Desmos. Okay. Which means you have to be mindful of what your answer choices may be. Okay. Because this is a multiple choice test, we do not know if you're going to get a log with natural log, you're going to get a common log, or you're going to get a log of the same base that you have, which means that we have to be comfortable using all three. Make sense? Because It's all in the hands of AP Classroom, which one they present with us. Will it be multiple choice? Yes. And we'll just figure it out from there. But let's start with it by hand. So by hand, that goes back to us switching our X's and Y's. So you remember us switching our X and Y. So our X is currently here, Y is currently here. So to find it by hand, it becomes, I can write. X equals 1,000, 0.587. Okay, I can't squeeze it in. I thought I could. I was going to make it fit, and I have no clue why I made the 1,000 so far from the equal sign. I kind of set myself up for that. X equals 1,000 times 1.587 to the X. And we're going to go back through the steps to the Y, not the X. You see nothing. All right, sad mapping it. What am I going to do first to start getting Y by itself? Is there anything you're adding, subtracting away? Nope. Is there anything I can multiply or divide away? And that would be 1,000. Okay, so I divide, and I'm now left with X divided by 1,000 equals 1.587 to the X. How do I cancel out an exponential? The log of the same base, right? So I'm going to take the log of 1.587 X over 1,000. And that now is my new equation. That's now my inverse, my log model. Okay? So this is by hand. Questions by hand. Hopefully by now we're all comfortable with the inverse of an exponential is a log of the same base. Okay? Now, let's go to Desmos. In Desmos, if you choose to do this, your table is switching. So your table that you're putting in for Desmos, because it's inverse, that means your X's and Y's are switching. So your table becomes 1,000, 0, 2,000, and 1.5. Because inverse literally means your independent and dependent do what? Switch. So your X and your Y are switching roles. Okay? So we're going to go to our table here. I'm going to add the table. And this time I'm putting in 1,000 is at 0. 2,000 is at 1.5. Going to adjust the window. And I'm going to run a X regression model. What kind of regression model do you realize that it gives me? It gave me a natural log. So the regression model for logs on Desmos AP Classroom is set to give you a natural log. And if that answer choice isn't a natural log, then we have to type it in so that it can be a log model, because it's automatically set to give you a natural log. And if it's like, oh, you're like, oh no, yeah, that's not what I need. I need log. And if you need log, then you're going to have to adjust it, okay? So in order to adjust this, what do? Well, we have to type in our own log model for ourselves, okay? So by typing in our own log model, we have the, I forget what it's called, but I'm just going to write it. We have y1 tilde. That's what it's called. Tilde. And we're going to type it in so that we can get a log model, which is going to be A plus B log of x1. Okay? When you notice there's going to be some subtle differences. Did the A change? No, but what changed? The B. So for Desmos, you have to switch the table and you can run the regression, but the regression is going to automatically give you natural log. If the problem is not, if your options are not natural log, then you're going to have to, let me write it out for you. you're gonna have to use y1 tilde a plus b log of x1. And that's going to force Desmos to give you the log model of it. Okay. What I want to show you guys is that they're all equivalent forms. So no matter which one you're using, they're all equivalent forms. So we're going to copy this one so I can save it. I'm going to close out the table. So we have that one. We have to write this one. So we're going to write y equals, and I'm a cheater. I just copy because I don't want to have to type. I don't have to. Plus and log of x. And what do you notice? They're exactly the same. We're also going to type in the one that we solved by hand. So by hand, we got y equals log shift dash 1.587. That can be exact 4. We want to keep the thing the same. And we got x divided by 1,000. What do you notice? They're all the same. They're all equivalent forms of the inverse of this guy. Okay? So if I undo this, undo this, undo this, they're all going to be inverse. They're all going to be inverses of this guy. So let me look. Oh, look. There they are. There he is. Okay. Oh, look. You're there too. Oh, look. You're there too. Okay. That's because these are all equivalent forms of the inverse. Okay. Log is like a little magical wizard. Say for exponentials. They can take different shapes and still be equivalent values. Okay. Which one you put depends on what your multiple choice options are. Does that make sense? Which one you put is going to depend on what your multiple choice options are. Whether you're putting natural log, common log, or the log of the exponential base. And because I don't know which one you're going to get, my job is to show you all three. Okay? All right. Again, these are all, that's what we got. This is what the regression model gave us. And then this is what we ended up with our rule. Okay? Again, all are still inverses of the original one. Capiche? Okay. So with that being said, the next part asks you is what does using the inverse model, what does G of 1,000 mean? So we're looking at our inverse. What does the 1,000 mean? So if I plug in 1,000 to our model, does it matter which one I use? Nope, it's not. So we're going to just select one. If I type in 1,000, what does it mean? Well, 1,000 means that that's my initial population, right? It's what it started off with. So in 1970, not population, transistors, in 1970s, there was only, the capacity was 1,000 transistors. Does that make sense? And that's because when I type in 1,000, it gives me 0 as my year, which is 1970. So it says, what does it mean? It means in 1970, only 1,000 transistors was capable. Okay. Now that I have my inverse model, can I calculate in what year roughly was 3 million capable? Could I calculate when about 50 billion was capable? Yeah, I can. So when I go back to the computer calculator, I'm going to go to my table and I want to know, when did I have 3 million? So 3 and 6 zeros. 1, 2, 3, 4, 5, 6. So how many years later from 1970? About 17 years later. So what year? In 1987, they were able to have about 3,000 transistors. Does that make sense? And were the computers and technology better in 1987 compared to 1970? Heck yeah, way better. Okay, what about 50 billion? So 50 billion is going to be 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 50 billion transistors was at 38 years later. So what year are we in now? 2008. So by 2008, we were at about 50,000 transistors. So when it says, what does it represent? Remember, we're going back to what each one meant. So when we're talking about the number of transistors an integrated circuit provides is a good measure of the speed of the computer, right? So the computer speeds have drastically increased based on its growth, right? So 1987, the speed was at about 3 million transistors. I always forget a zero. Was capable, which helped with our computer processing speed. And then by 2008, we're now at 50 billion transistors. And as a person who has watched the growth of technology in the span of her life, it has been a very interesting experience to say none the least how quickly technology has changed. Okay. All right. Questions, comments, concerns about exponentials, logs, their inverses of each other, the relationship to each other, and using Desmos as a tool to apply this information.